Hey, what's up, guys? Welcome to my algebraic geometry videos. Okay, so previously I have one detail that I have not yet explained. So let me just quickly explain. So previously I say that so you can construct a fine skin as construct a fine skin. And so one definition is that you already know that one definition for the structure sheaf is that you already know that your fine skin can be there is a basis called distinguished open set, as I proved in my previous video that this DFI forms an open set, and as an open set is basis. And you can also check that the one definition for the structure sheaf is that for each DF, then I can define AF to be a ring localization in F. So it's A divided by F of N, where A is belongs A. Okay, so now I define a structure sheaf on a basis. So in general, open basis. So in general, when I define this, then the O of X is already defined. It's already defined, already well defined, and the Y is well defined. So you can check out my other videos that I will prove that this OX is really a sheaf. Okay, so one can show OX is really a sheaf. Okay, but one definition, and I also say that if you go to the stalks for each prime deal, that this is exactly AP. Okay, AP is basically A divided by B, where B do not belongs to the prime deal. Okay, so if this is true, then this makes the OXP, or basically the OX, as a not just a ring space, but a local ring space. Okay, so local ring means that each OXP is a local ring. And the reason is that you can check out my other videos, is that one can show this AP is a local ring because one can show that this PAP is the only maximum ideal of AP. Okay, so the missing part that I have not yet explained is that how you can show that the stalks, how you can show show the stalks of the structure sheaf is indeed AP. If your definition is this, right? There are other kind of definition, but one simple definition is that, oh, I create a basis. I say oh, there's a basis, and I just define out my structure sheaf on each basis, and I say, oh, this is done. The rest is just defined to be you using a sheaf axiom. Okay, and how should I show this? This will give the stalks to be the prime deal, which to be the ring localized at that prime deal. Okay, so this is the mixing part. So I want to say I want to develop this goes to why the stalks is basically AP. Okay, so I think once you have this, then you have all the details. You know how to define the structure sheaf and why the stalks is this, and you know why this is a sheaf. So basically, you know everything about, you know, the construction and all the details about a fine skin. I mean, at least abstractly. Okay, so OXP is defined to be, let me just explain this. Right, you can take the P belongs to U open set, where U is open, and they'll define to be the sheaf OU. Okay, and simply speaking, this is just defined to be the disjoint union of U, and the U is open, and the O of U, and the quotient something, right? Quotient is this is the colimit. Okay, so this quotient means that wherever you see the let's say AB, right? If you have this A, let's say A equivalent to B, right? If there's a neighborhood. So now since I already proved that the distinguished open set is a basis, so I can freely just only focus on the distinguished open set. Okay, so if I have this DH, such that if there is an open neighborhood DH cover P, let's say, right, cover P, such that if I make A, right, so this is the element of a sheaf, right? So I can say A restricted into the D of H, such that if D of A restricted to DH is the same as B restricted to DH, then I would say that A equals to B, or A equivalent to B. So basically, this is the same as, right, it's just a definition. Okay. And, okay, so obviously that, so this definition just tell you that wherever you see these two elements, they're restricted to some open neighborhood or some distinguished open set. If they are the same, then this is the equivalent. Okay. Okay. So obviously that I can define this OP OXP, right? Only on a distinguished open, only focus on a distinguished open set. Right, so I can write as limit as P that belongs to D of H of D of H. Okay, so this just tell you that I restricted myself to the distinguished open set, and I take all the priority which covered by some H, and I collect all these sheaf ring localization. This, then my claim is that this is what we're gonna to prove here. This guy is basically the A P. Okay, and then this is A of H, right? So A of H. Okay, so basically our gonna to do proof is this, or P belongs to D of F, and AF map to, let's say, AP, and that's okay. So this is what we're gonna to prove. This is what we're gonna to prove, and we want to prove that this is isomorphism. This is the same as P do not, P belongs to D of F. This is the same as F do not belongs to P. Okay. So I take all the, so I take all the F do not belong, I take all the F do not belongs to P, and I take this sheaf, this ring localization, and using a colimit definition, and I define, and then I have the natural ring homomorphism to AP. Okay, the definition is very simple. So this ring homomorphism phi is defined to be if somebody give you any element in AF, like A, you just directly map to A. Okay, because F do not belong to P, right? So if I write A to be F of N, sorry, A divided by F of N, then map into AP just using the same thing, A divided by F of N, because F do not belong to P, right? So A divided by F of N will be AP. Okay, then you can check this is well defined. Okay, so the goal is to show this phi is isomorphism. Okay, hopefully everything is clear. Okay, so phi is homomorphism. This is simple. Check by yourself. The first one is phi is surjective. This proof is trivial if you understand the definition. If phi is surjective, that means that AP, right? So let's say if I take a very simple, very trivial, right? If I take A divided by P belongs to AP, I know that B do not belongs to P, right? That means that so I can choose choose AB, right? Because AB B do not belongs to P, right? So I can choose AB. I can choose an element called A divided by B in AB, because B do not belongs to P. So if I localize a B, I get A divided by B. Okay, so obviously that I can choose A divided by B in AB, then by definition, our phi of AB will be A divided by B in AP. Okay, so this is surjective, trivial. Okay. Now, we want to show that this guy is injective. Okay, so this may be a little bit tricky. Injective means that if I take A divided by F of N 0, now 0 in AP, which means that so this is A divided by Fn. So I just say that it's A divided by F of N is 0 in AP. Okay, so this means that there exists a G do not belongs to P, such that the GA is 0. Okay, so this is the definition of ring localization. But if this is true, then what you're saying is the following. Right? You are saying that if this element is X, you can in a colimit, right? You can make a map from AF to AGF by just sending each element A divided by F of N to the same thing, right? To just A divided by F of N. But you need to return as GF, right? So you can just take GN and GN. And this is well defined. Okay. But if this is true, then you are saying that the AG GN minus 1 GFN, which is 0 because GA is 0. Okay. So this tells you that if you find the element which A divided by Fn is 0 in AP, that means that this A divided by Fn is 0 in AGF. So by the definition of colimit, you need to preserve this map, right? So if it's 0 in AGF, then it keep maps into this AP and still 0. Okay, so this guy map into 0. Okay, so this proves that this phi is injective. Okay, so yeah, I think this is the missing part of the thing that I have not yet said this. So yeah, see you guys next videos.